So, any questions about anything before we get to the material for today? If not, then let's just get after it. The picture here is our stickman drawing of a CPU and a computer showing that we have a thing called a program counter, which is an address of a memory location where the next instruction to be fetched from memory and executed is. And so the computer, in the absence of any jump or branch instructions, simply marches through memory, picking up the next instruction and incrementing the program counter by the appropriate number of bytes based upon the length of the previous instruction, obviously, to get the next instruction out of memory, sequentially plowing through the code. And then we have a bunch of registers where we pull things out of memory and hold them in these registers in order to do things to them. And then we execute instructions that manipulate the values that are in the registers in some way, multiply them, add them, shift them, do whatever it is we're doing to them. And then we have instructions that store the registers back into memory at some particular location. And so the side effect of executing some instructions on the computer is to light up the condition code bits. So if we have overflow or things like that, that we can detect that. And then we can use those condition codes in doing conditional branches. So if this condition code bit is set, jump to this location, otherwise fall through to the next instruction. And so you can implement if statements and all those kind of things. So that's how we actually can implement all those algorithms, is based on the conditional branches. So in the Intel processors, you can't directly manipulate things that live in memory. You have to pull them into the registers, do things to them, and then shove them back into memory with another instruction. Some computers, some mainframes, etc., you can actually have instructions that say, oh, go to memory at some location, pull that in, add one to it, and shove it back into memory or something. So they have instructions that look like they're directly manipulating memory, although in reality, they're pulling the thing into the CPU, do something, and then shoving it back, all as one sort of massive instruction. So those are older, really super dyed-in-the-wool CISC complex instruction set type computers. The Intel is technically a CISC computer, but it's a really kind of weak version of a CISC computer compared to some computers like the old VAX mini computers that had just gazillions of instructions and addressing modes and things. So anyways, that's our basic model of a computer at this point. Pulling instructions out of memory, executing them, manipulating things in the registers, moving things back and forth between memory. And so then we have this little sample snippet of C code, some little simple function, once again, where we want to pass in two integers, add them together, and then return the result. And so we want to sort of see, well, what might the compiler emit as assembly language that accomplishes this? And so we're looking at this code over here that implements this function. And we'll see that these first two statements have to do with the calling convention for how we're implementing the semantics of the C function call on the computer. And we'll discuss that today, later. Don't worry about it right now. And then what they're really showing you is this instruction here: move long word, and long word, the L at the end of the instruction, right, means 32 bits, 4 bytes, because these started out as 16-bit processors, and the word was 16 bits. When they made the 32-bit one, they called that a long word. And then when they got to the 64-bit computer, they have 64-bit things. They call that a quad word. So you'll see a Q sometimes on the end of instructions on the 64-bit machine. So we're at moving, and this addressing mode here, what that means is the EBP register, and all our register names start with a %. Take the EBP register, contains an address, and the parentheses is sort of the counterpart of the C splat operator. It means go to that memory location pointed to by what's in EBP and get the contents of it. But rather than going to what EBP points at, what I really want is 12 past the address that EBP points at. So this is a displacement. We'll see that later. And that's actually being used to pick up this Y parameter. Going 12 past what EBP points at is getting the parameter Y that's being passed into this function. And going 8 past is getting this X parameter here. And we'll see how that works in more detail later. And it's adding the two together, right, into the EAX register. And then it leaves with the return. And the way you pass a value back out of a function in the C calling conventions on the 32-bit Intel processors, you leave the value in the EAX register. That's how you're returning that integer there. So it's just a little quick sample of what you might see implementing that little function there. So we have the ability to manipulate data of 1, 2, and 4 byte and 8 byte longs as well, integer data. We have floating point. You've seen the 4 and the 8 and the Intel internal 10 byte thing we won't talk much about in this course. We'll just use our ints and our doubles in C. But the computer, all it can do is pick up things of 1, 2, 4, 8 bytes, move them around between places and do things on it. That's all it can do. It has no concept of anything like in high-level languages. We think about arrays and records, structures, that sort of thing. None of that exists on the computer. That's just on the high-level language, and then we map that on to the architecture of the computer, and we'll see how we do that. So assembly language operations can perform arithmetic functions on registers and not on the Intel. You can't directly perform on data in memory. You have to move it into the register before you do something to it. You can transfer data between memory and a register in both directions, right? And you can transfer control. You can jump to some address in memory and execute the instructions that live there. Or you can do a conditional jump based on whether one of those condition code bits is set or not. And so that's the basic capabilities of the computer. If we thought about the instructions lying in the memory of the computer, just a bunch of binary stuff lying in there, then what this is trying to say is that the assembler translates your assembly language .s file into the object file, and the object file is these opcodes that the computer can understand and execute. And the linker, of course, is resolving external references and linking in library code that you didn't have to write, like printf, things like that. So if we look at this one C instruction, I want to add two things together and put it in T. That might correspond, say, to this one assembly language instruction here, adding some stuff into the EAX register. And then when it gets down into the actual codes that the computer is going to see, it might be this stuff here, 345.8, right? This is indicating that that address, it would have that contents or something, right? So we can disassemble object files with a program called object dump. So if we had some executable file P we could run the object dump thing. And so it'll go in and it'll read all these opcodes and it'll turn them into the corresponding assembly language mnemonics that represent doing those instructions, right? So this is a disassembly of the object code. The fact that it shows the sum here comes from the symbol table information from the compiler that got saved off, associating a name from the source file, source language, with an address. The function sum lives at this address ultimately. So the disassembler can get that information too and plug that in and say, oh, this is the beginning of this function sum in your program. That isn't per se part of the object code, but it's getting that symbolic information that can be saved, doesn't have to be saved when you do the compilation process. So in addition to disassembling an object file to see the assembly language, we can also go into a debugger like GDB, GNU debugger, and feed it the object code, and then it can show us the assembly language for the object file. And we can, with the debugger, walk through executing instruction by instruction and then interrogate the contents of the registers and memory locations to kind of try to follow what's going on and debug maybe something that isn't working right. So your lab next week will be learning the basics of using the GDB debugger, which is a skill that you will need forevermore in your career. You might as well get started on it now and learn it. And you'll hand in a product as a result of that lab that you do learning the GDB debugger. You'll correct some bugs in a program we give you that's full of bugs. And you'll hand the corrected program in, and you'll use the debugger to, trace through and find the bugs and stuff. So it's an exercise in learning how to use the debugger. So watch out, because that's due late Friday evening. You have to have that finished and submitted from your lab if you didn't finish it on the day that you had your lab. And so next Friday is kind of like the equivalent in the stock market of what they call triple witching hour, where all the future contracts come due at the same time. Next Friday, you have your lab exercise due, you have a homework set due, and you have your first project due. So watch out, things are getting busy. So here's showing that object dump programs know a whole bunch of different formats that are used in different operating system environments for how they store their executable images for things to be loaded in and executed on the computer. And this is showing we could just take the Microsoft Word executable and point it at the object dump program at it. It would disassemble it. We could read this and see exactly how Word works. You can, quote, reverse engineer somebody else's code by doing this. Of course, you have to read it at the assembly language level, not the source language level. But it can be done. You can take that code and figure out how it works, right? What they're doing. So now we want to look at some basics of registers, operands, and things. So we go to the next lecture, talks about that. So here it is. Here's your 32-bit Intel architecture. Here's all the registers. You have a whopping 8 registers. That's all you have on this computer. When we get to the 64-bit guy, we'll see that we have 16. We have twice as many registers, and they're twice as wide. So the thing started off as a 16-bit processor, right? In the old 8086 days. And so the register AX was 16 bits wide, and you could refer to the high byte or the low byte with these names. And then when they made it 32 bits wide, they just stuck an E in front of the name for extended. And so you can still use these old names for AX, AH, AL for the pieces. It's just the right portion of the 32-bit guy. When we go to the 64-bit guy and it's twice as wide as this, they'll call it RAX. But you could still refer to the right side, the 32 bits, as EAX. So you get the idea, right? Well, why do we have all these goofy names, AX, CX, BX, SI, DI? Well, that has to do with the fact that on earlier versions of the processor, they didn't have a whole lot of massive density like we have now on the silicon. And so if you wanted to do, say, something like multiply two numbers, maybe you had to put the first one in this specific register and the second one in that specific register, and then the result went to this other specific register. In other words, you couldn't just use any combination of registers for the operands and the result. And we call that a non-orthogonal instruction set. And so that's a pain in the neck when you're writing assembly language, right? And you have to remember, oh, these registers have these specific uses. And so later, as we were able to build more and more dense circuitry, we could make more and more connections between the registers through the functional units, right? And so we can get rid of some of these non-orthogonal aspects and say, oh, you want to multiply? I don't care. Put it in any register, and then we can move that into the multiply circuitry for you. So later processors tend to be more orthogonal, and older ancient processors tended to have these restrictions on what had to go where in order to do an instruction. So that's where these idiot names come from. It's just a leftover from what their functions were in the old non-orthogonal processors. Source index, destination index, that sort of thing, right? They don't really have those meanings anymore, but the names, we still just use the names. So the only two that have sort of a special meaning in the 32-bit processors are the ESP, the stack pointer, and the BP, the base pointer. And we'll see that we use these registers in a special way, not just as general purpose registers to hold things that we're manipulating. They have a specific function that's involved in implementing the calling conventions for how we implement the calling conventions for subroutine calls and those sorts of things. We'll see in a minute. So when we get to the 64-bit one, the BP will go away, and the only one that'll have any special significance that's used for a specific purpose will be the stack pointer. So what can we do with these registers? Well, we can do things like move is a move instruction, right? And the L tells you the size of the operands that you're operating on. And the L stands for long word. And so long word means 32 bits, remember, because the original ones were 16-bit and they made a 32-bit version. So they called that a long word. When they get to the 64, they'll call it a quad word. So the last letter of the assembly language mnemonic for an instruction typically is going to have a last letter indicating the size of the operands that you're operating on. So this is saying move long word, and this was specify the source to some destination. And that's the way it works in the GNU assembler. The source comes first and the destination comes second. If you ever use the MASM, the Microsoft assembler, they're backwards. The destination would be first and the source is different. It's generating the same opcode on the computer for the same instruction, but the mnemonics, the conventions in the assembly language are different. So in ours, the source is going to come first, the destination is going to come second, which makes a lot of sense. You read left to right, right? So then what kind of operands can we have? Well, the first one that we show here is what we call an immediate operand. And whenever you write a constant down in assembly language, you put a dollar sign. Oh, this is a constant. And then we're using the same conventions we're using in C to say OX means this is a hex number. Or we could write dollar sign minus 533. It would be a decimal minus 533, right? Base 10. So it's just like the C constant, but you got to stick the dollar sign in front of it. And so this constant is going to end up either being a 1, 2, or 4 byte entity. Later on, we'll see we could actually have 8 byte ones. But so that's one kind of operand that we could have, right? And so then another operand type we could have would be a register. Just pick one of these names, could be the thing we're dealing with, or it could be some memory location. And the way we express that is put the parentheses around the name of the register, and that's sort of the counterpart of our splat in C, right? Saying, oh, EAX register has a number in it, and that number is the address of some memory location. I want you to go to that memory location and get me the contents of it, right? So if I left the parens off, I would say, if I wanted to move EAX, if I put it as a source, it would be moving the contents of the EAX somewhere. But no, I don't want the contents of EAX. I want the contents of the memory location it points at, right? So let's look at some examples of the combinations. Here's all the ones that make any sense, right? You can move an immediate, some constant, into a register, right? You could move a uh, immediate value into some memory location. That would be the location pointed to by the address in the EAX register. Okay. You could move a register into another register. That would make sense, right? Or you could move a register into some memory location. Or you could move a memory location into some register. And so those are all the combinations that you can have. Notice the one combination that's kind of missing here. You can't move a contents of a memory location to another memory location. I couldn't put parens around the EDX here. The Intel processors don't have any memory to memory move instructions like some other computers do. To move something from one location in memory to another, you got to suck it into a register and then push the register into memory, right? Like this. Two instructions. So you only in the Intel computer ever get to touch memory at most once per instruction cycle. So that'll be good to remember. So you don't have the combination where you touch memory twice. You touch it at most one time as the source or the destination. And what you're putting in it could be immediate, could be a register, or you could be pulling something from memory into a register. Is everybody cool with this? So they're showing you sort of counterparts in sort of pigeon C over here, what that kind of thing kind of looks like. Putting a constant in a variable, putting a constant in splat P, that's dereferencing the pointer P. Put it in what P points at in memory, right? Same thing as this. Any questions about that? So these are some basic assembly language instructions to move things around between registers or memory locations. We have other addressing modes, right? We've seen this one where you put the parens around it. Say, go to the location in memory that ECX is pointing at, pick the contents up and stick it in this register. But we can also put a displacement in front of the parenthesis there. And we saw that in the little example previously. They were going 8 past where the base pointer pointed. So this is saying, oh, I really don't want to go to the location pointed to by R. I want to go this many bytes past the location pointed to by R and pick up what lives there. So this is a displacement. Go 8 locations past where BP is pointing, pick the contents of that up and put it in the EDX register. Good enough? So now we have a little simple function call in C where we're going to pass in the address of 2 integer variables, and we want to swap the contents of the 2 variables, right? So in C, we have to manually pass in the addresses, unlike in a lot of languages where the compiler has to work for a living. In C, you got to yourself say, oh, this is a pointer to an integer. Pass me the address in of the thing you want me to mess with, and I'll manipulate it. Now I'll do the splat thing. Give me the contents of what that thing points at. Put it in this temporary variable. Give me the contents of what this guy points at. And now I'm going to stuff them back in memory in the opposite locations. Put the T1 in where XP is, the opposite one. Put the T0 in the YP. So I've swapped the contents of those 2 variables that you passed me the address of, right? Everybody see how the C code works. Well, what would that look like if we compiled it and we got the assembly language? Well, the first thing is there's this little chunk of code here called the preamble, and a little chunk of code here called the epilogue that have nothing to do with the body of the function that you're trying to implement. They're just setting up the calling conventions, implementing the semantics of how we pull off the function call and the return from the function, right? And this will be a little weird looking at first, but in a couple of days, it'll be just as plain as adding 2 and 2 and getting 4 to you. The 32-bit C calling conventions for calling the function are mapped onto the architecture of the Intel computer by a set of conventions that we use. And all the compilers that compile C programs use this same set of conventions for mapping a C function call onto the architecture. First thing we do is we save a base pointer register on the stack. Now, the stack, we have this special register called the stack pointer, the ESP in the 32-bit world. And it points in memory. And when we do push operations or pop operations, it behaves like a stack. When we do a push, it takes what we push and sticks it at wherever the stack pointer is pointing in memory, and then it increments the stack pointer. But actually, in the Intel world, what it really does is it decrements, because the stack in the Intel processors grows from high memory locations towards low memory locations. So what this push is doing is it's taking the contents of the BP register, sticking it at the memory location ESP points at, and then subtracting 4, because it's a long word that you pushed, 4 bytes, from the address that the stack pointer points at. If I did a pop of something, it would pull the contents off of the stack where the stack pointer is pointing, and then would increment by 4. So see, this ESP thing is behaving like a stack in memory, pushing things on it and popping things off of it. And so that's why we have this reserved function for this one special register called the stack pointer that behaves like that when you do these push and pop instructions, right? So why we are pushing the EBP will become clearer later, but this has to do with how we're establishing the calling conventions to implement the semantics of a C call, right? We save off the base pointer, then we take the value of the stack pointer, put it in the base pointer, and now we've established the environment we need for the local function to execute in using the stack. So then this business here of pushing the BX register has to do with the fact that there are certain registers by convention that the caller expects to survive unchanged across a call. And those are called call E save registers. That means the call E If he wants to modify it, has to save it and then restore it back to what it had, because the caller expects it to have the same thing in it that it had when I called you. Caller save registers are ones that if the caller wants to survive, it's on him to save them before he calls me, and I'm free to clobber them without saving them in my code. So we just by convention divvy up the registers in half and make half of them callee saves and half of them caller saves. And we'll see which ones those are. But I'm going to want to use the BX register down here in this code. So that's why I had to save it. I can't destroy what it had from the caller's point of view. I got to save it and then restore it before I leave so that I can use it for my purposes in here. So that's why that you see that push of the BX register. Now this business here where it says move long word 8 past where the base pointer is pointing is actually going and getting this first parameter, and going 12 past where the base pointer is pointing is reaching up and getting this second parameter. And we'll see how that is set up by the caller so that they're living in those locations. That's how he's passing these things into us, is by sticking them on the stack, and we're going and getting them off the stack because we put the stack pointer into the base pointer right here, right? So we're reaching back up into what you later will see is a thing called this parameter staging area, which is the lower part of his activation record for his function. So this is the scheme that we're using to pass those parameters in, and we'll elucidate this in further detail in a moment. So this is using that displacement mode of addressing to reach back up the stack and get those two things. Well, I put it in these two registers, and what have I got? I've got the address of some variables now. So now you see the parens is dereferencing those addresses to get the value, putting it in these registers, and then I'm storing the values back into the locations in the opposite place. There's my swap function. I restore the BX register, restore the BP register so that they have the same thing in them they had in them when the caller called me, and then I return the call instruction that made us land at this address associated with swap, this first instruction here. The side effect of the call instruction is to save off the return address on the stack. So the call instruction is sort of like a combination of a jump, a branch, and a push, right? And what it pushes is the address of the next instruction in memory right after the call instruction. That's the return address. So when you do the return, you land back on the instruction right after where the call instruction was. So that got stuffed onto the stack as a result of the call instruction, which then landed here on this address. And so when we do the return, we're popping that return address off the stack and branching there to get back to where we were called from, right? So we'll see this explained in further detail here. The preamble code, which has to do with the calling conventions and how the registers are used to simulate the behavior of a function call and return. And then the actual body of the code, which does whatever it is we're trying to accomplish in the code, right? So this stuff is going to be pretty much the same, except maybe we wouldn't save the BX because we didn't need it in the body. But these first two statements are all going to be the same in every function call in simulating a C function call in the 32-bit architecture is always going to look like this. Push the BP, move the ESP to the BP, and then it's going to say pop EBP return. Those are all going to be the preamble, and the epilogue are always going to look like that to implement the calling conventions of how we create the call. Okay, so here's more detail what it looks like. Here's our stack. And so when the call happened, when the caller was getting ready to make the call, he stuffed the parameters onto the stack, right? So they're sitting there. And in the C calling conventions, note that if you go from bottom to top, they're left to right. Some other languages do it the other way, where the right one is at the bottom. Pascal does it the other way. So C calling conventions say, okay, you stick the parameters on the stack in that order. Then you do the call instruction, which stuff the return address on there. And now you landed on the code for the function being called. And the first thing it did was it saved the BP by doing a push. So there's the old base pointer that the whatever value it had from the caller's point of view got saved. And now by doing that push, the stack pointer marched down here, right? And so we took the stack pointer and put it into the BP register. So BP points right here. And then after that, we saved the BX off because it was a callee save register. That isn't part of the calling convention. It's just because we need to use it here in this function. Okay? Questions about this stuff? Blow by blow, they're going to show you step by step what's going on here. Here's all the registers on the computer. And in their example, they have something that isn't particularly realistic. These addresses of the variables that we're passing in, the two things we want to swap, they're showing as having these addresses 120 and 124, which are real close to where these addresses for where the stack lives. In reality, they would be way the heck over somewhere else in memory. They wouldn't be anywhere near where the stack lives, but it wouldn't fit in the picture if they did that, right? Of course, they could have just broke that off and showed some memory over here. It would have been more realistic. But they're showing them as living at these locations that are kind of close to where these stack locations are, just so they can draw the picture easy in the example. But that isn't particularly realistic at all. Nor are these little teeny low addresses. They would be big, huge addresses. The stack starts way the heck up in high memory. You have a big monster address there. But given those allowances to make the picture look simple, it behaves like this. When we did the call, the return address got dumped on the stack. And before we did the call, we stuffed the parameters we wanted to pass to the guy on the stack, right? That's our XP address and that's our YP address, right? And there are these addresses up here. That's the contents of those addresses. Did the call, the return address got stuffed on there. The stack pointer was then pointing at this location, right? And then we saved the BP, right? And then the stack was pointing at this location. And then we took that and stuffed it into the BP. So let's see what happens. After we did all that, our first instruction here says go 8 locations past where BP points. So where does BP point? He's pointing right here at this line that's at the bottom of this. He's pointing at that address right there, right? Because we did the push to BP and then we saved BP into the saved SP into the BP. So the stack pointer was pointing here when we saved it into the base pointer, right? So if we go 4 locations past that, we're pointing at the return address. If we go 8 locations past that, we're pointing at that first parameter. So this is picking up the first parameter off the stack and putting it into the EDX register. Going 12 back will get you the second parameter. Why 12? Because, well, these are integers that are 4 bytes long. They each take 4 bytes up in memory sitting in the stack, right? So that's how we're getting the parameters that the caller passed into us, is by going back up. And if we always do this little 2-step thing of pushing the BP, put the ESP in the BP, then it is always going to be the case that the first parameter will be 8 bytes above where the base pointer is pointing. The second parameter will be however 8 bytes plus however big the first parameter was. If it's an integer, you go along, it would be bigger, right? So the offsets that we're going to get to these guys always start at 8, but the second one, if the first thing I passed was a character, the second one would be not at 12. What the return address is. Okay. Well, Dorothy wants to get back to Kansas, right? So I'm in the caller. I'm about to call some function, right? And so I have to hand the function in some way that I'm going to call the address where it needs to come back to execute the instruction after the call instruction to get back home, right? So the call instruction does that for us. It takes the address that is the address after the call instruction and pushes it on the stack and then does the branch to the address for the routine that I'm calling. So it does those two things as one thing in the call instruction, right? You can think of it as a push and a jump. So then that's sitting on the stack. So when I return from the subroutine, he can use that to get back home to Kansas, right? He can go back to where I was called from because the same function could be called from 47 different places in the program, right? And so the return address is different each of those 47 times, but I have to hand it to him so he can get back to the one from where I was called, right? So the return address got dumped onto the stack as a side effect of the call instruction, which got us to the code for the subroutine, the branch, right? So these are getting the parameters. So this is just a set of conventions for the 32-bit Intel processor called the C calling conventions. How do we simulate the semantics of what a C function call is supposed to look like, right? We have to map it onto the architecture of the computer somehow and use the instructions that the computer has to behave like what that's supposed to mean when we write that down in our high level language. And so this is how it actually gets implemented onto the computer, right? Passing the parameters on the stack, reaching back up from this base pointer, this many locations to get the first parameter, the second parameter. So then the code is relatively obvious, right? You are going to grab these memory locations, right? You grab the second parameter and it puts it in the CX register. And what are these parameters it's grabbing? They're the addresses of the variables I want to swap, right? And then you go to the next instruction and it says, take this address that's in the DX register, which is the X guy, right? And go grab what's at that memory location, right? Which is 1, 2, 3, and put it into this register. The next one says, go grab what the Y one points at, put it in the EAX register. So there they are sitting in these two registers. Now we take what's in the EAX register and we stuff it back at the memory location pointed to by EDX. So we're going to swap them, right? So then we put the other one back in over there. So they're swapped now, right? Have other addressing modes that we can use on the Intel computer. And this is the full-blown, this is about as complicated as addressing modes get on the Intel computer. So the Intel computer is technically a CISC computer, complex instruction set computer. But frankly, as CISC computers go, it's a pretty wimpy one. Real classic CISC computers, like from the mini computer era, like a VAX computer, had just maybe a dozen different addressing modes that it had. And it had memory to memory moves and all those kind of things. The Intel computer is kind of a, yeah, stuck its nose under the camel, stuck its nose under the tent just like an inch into the sys computer world. It has, this is as complicated as its addressing modes get. So how does this addressing mode work? Well, this is basically going to simulate subscripting into an array laying in memory. It's what this addressing mode's purpose in life is. This S you can think of as the size of the elements of some array. Say it's an integer array. These would be 4 bytes a whack, right? And you can think of this one in the middle, the RI, as the index, the subscript that you want to get to in the array. And you can think of this base guy as the address where the array begins in memory. So if I had 4 sitting in this, way this instruction works is it takes the 4, multiplies it times the index, and adds that to the base. Well, doesn't that generate the address of the ith element in the array where each element is S big, right? So that just is behaving exactly like what I want. If I made this first thing point at the beginning of an array and I put the index element, indexing from 0, and that's why you see C just directly reflecting the computer's instruction set saying, if you put 0 in here, then you're getting the first element in the array. You put 1 in here, you're getting the second element in the array, right? So the trick is this S thing isn't really being multiplied times the index. A multiply operation in the circuitry is real expensive in terms of clock cycles, right? Compared to, maybe like 4 to 8 clock cycles or something. I have to look it up. It's at least 4. So anyway, we're not going to do a multiply. What we're going to really do is, we're going to do a shift, right? And that means that this S thing is always a power of 2. So the scale for the size of the elements is always a power 2. Well, that's okay because those are the data sizes we use on the computer. 1, 2, 4, 8. That's the chunks that we move things around in. They're always powers of 2. So what this instruction really is in this assembly language, you write down 4 for S. What you really get is shift 2 of the thing in left of the thing in the middle. So you're always writing a power 2, and it's really shifting, by log base 2 of what you're putting in there. Does that make any sense? Okay. So what this addressing mode does is it takes that theoretically, in theory, multiplies it times the one in the middle and adds it to the one on the left. Sort of simulates exactly what you want to subscript into an array. And then you can optionally have this displacement over here, which when we start looking at records, structures, if you wanted to have an array of records, this would get you to a field within the record. So boom, in one thing, we could have an array of records laying in memory, go to the right location where that record begins, and then go to a field within the record. And so that's why that addressing mode exists. They don't just invent these things to implement on the computer because they look cool. They implement them because they need them to map some concept from a high level language onto the architecture of the computer and have something that behaves like that, right? So this is essentially the addressing mode that implements array subscripting for us, right? But we can use it for all sorts of other things too. Okay. So it comes in a lot of combinations, and all they're showing you here is you can leave pieces out. You can leave the displacement off and the scale factor, in which case it's 1. And so all that would do is it would add the second one to the first one. And then the parens, of course, are saying, this is an address that I've generated. Go to that memory location and get the value, right? You could leave the scale off, in which case it's 1, and put the displacement. You could leave the displacement off and just do that, which you see used a lot, right? And in fact, you can leave the RI and the S off and just have the base. We've already seen that, right? So you got all these combinations of these addressing modes that you can use to talk about some location in memory you want to go to and either store something there or pull something out of there, depending on whether this is in the source or the destination operand, right? And so we have a question that says, is there a functional reason Intel machines forego these more complex memory addressing modes? Well, as microprocessors were crawling out of the cave and getting, a little more and more powerful, essentially they were reinventing the wheel because we had big, complicated mainframe and mini computers that had big, complicated instruction sets and did all kind of stuff. But you had big boards full of chips to implement that in the old days. And so when they were making little one chip microprocessors, trying to add more and more functionality to them, that was just a process of reinventing what we had already done 20, 30 years earlier on big computers that were the size of washing machines and refrigerators and stuff, right? So the microprocessors kept adding, add this capability, add this capability, add this capability, right? So you wouldn't have enough space on your microprocessor to implement all of the bazillions of things they had implemented on these big whopper mainframe computers, right? So they didn't implement the 8 billion different addressing modes. And so also the trend was toward less complex instruction sets, because that made it easier for you to optimize the instruction pipeline, which may not make any purchase to you at this point. Okay, so any questions about all these combinations of addressing modes? That's as fancy as it gets on your Intel CPU. Well, we're running out of time. So preview of coming attractions. Tomorrow we're going to look at the 64-bit computers, and we got twice as many registers and they're twice as wide. But we can still name the right side with all our 32-bit guys, obviously, right? Okay. So we'll do that tomorrow. So things are getting busy. Don't get behind. Nose to the grindstone, shoulder to the wheel this week, because next week, Friday rolls around. You got 3 things you have to have accomplished, right? The deliverable for the lab, the homework set for next week, the end of the first project. A lot of stuff, right? But there's a lot of stuff we got to learn in this class. So get busy. I would say knock your homework down for this week, get it out of the way so you can concentrate your time on your project after that. Okay? Should be up around page 200 or so in your reading. Don't get behind. Office hours are at 2 today. If I don't see you then, I'll see you tomorrow. Have a great day.